Hello AP Chemistry and welcome to Chapter 20, Electrolytic Cells. So, this is our Chapter 20 demo and discuss that we would normally do. You know what? We are going to do our best given the current scenario. So, first of all, for starters, electrolytic cells, what differentiates an electrolytic cell from a galvanic cell? Right. For an electrolytic cell, right, unlike a galvanic cell, these will all require power, right? So whether they're connected to a battery, whether we plug them in, whether the diagram for your cells just need to have some indication that there is an input of power somewhere, okay? In addition, what else is going to be different? Right, we're going to have a negative overall E0 voltage, right? And that's going to differentiate our cell. And, okay, but other than that, the process works the exact same way, right? All the same pieces, and all the same thought process, right? What's present and then what could happen, and that's what we're going to think about. Okay, so let's go ahead and look at question 1. So just like with the last one, we will work through parts of it together, and some of it I will tell you to pause and ponder on your own, and, just do the right thing. Okay, so scenario 1 says we have an electric current is passed through, so electric current tells you that it's electrolytic, is passed through a dilute aqueous solution of sodium chloride through inert electrodes. So let's talk about what all those things mean. What is the significance of them being inert electrodes? Right, that means that these do not react, yes? So as in whatever they're made of, it doesn't matter because they don't take part in our actual redox process, okay? And it says dilute aqueous solution of NaCl. What's the significance of that? Right, that means that relative to the amount of, say, H2O molecules present, the amount of solute present is less, right? There's not very much solute present compared to my solvent. And so that's just like a reminder to you, right, that these are probably not primary components in terms of deducing what's going to happen in my cell, right? Unless our data or our observations tell us otherwise, okay? Okay, so it says to draw the setup for this reaction. Let's go ahead and take a look, right? So here is our general setup, right? We have a Petri dish that is filled with our dilute aqueous sodium chloride. To it, we are adding some universal indicator, and we have a battery that has some electrodes connected to it. And that is the general setup for my cell. In just a moment, I'm going to get those electrodes set up. And then we'll go ahead and doodle that cell. My power source wasn't behaving, so you gotta make do sometimes. All right. So now let's doodle our cell, right? So we have a Petri dish. And here we have one electrode. Here we have another electrode. And these are connected to a battery, right? And we have our solution in there. All right, that's it. Now let's go check for our observations, right? Oh, write the half reactions and overall reaction for the cell. So let's see which of these are plausible, right? So thinking about our reduction reaction again, right? Let's look at which of these are possible, right? So there is no copper, there's no aluminum. This is in there, and we'll talk in a moment about why that's not plausible. Do we have chlorine gas? No, we do have some water. There is some oxygen present in the atmosphere, right? So why is this sodium one not going to be on the list? Right, so first of all, this is the most negative of our reduction processes, right? And odds are that one's not going to be the one that happens, right? Because if there is one that happens with less power input, that's going to be the more likely option, right? Second of all, if we were to produce solid sodium in an aqueous solution, what would happen? Right, that sodium would immediately react with the aqueous solution to then go back and form some sodium ions, right? Quite explosively and energetically, right? So unless we're talking about some molten sodium or something like that, molten sodium chloride, right? Or something that is otherwise not aqueous, this is not likely to ever be on our radar, okay? Which leaves us with the most plausible option as being this for our reduction, yes? As in most likely we are going to take 2 water plus 2 electrons, and that's going to give us some hydrogen gas and some 2 hydroxide ions, right? And this has an overall voltage of negative 0.83, right? And then let's go in the opposite direction, right? So let's clear off our table. Now if we're looking for our plausible oxidation processes, right? Again, there's no copper, no aluminum, there's no solid sodium, no nickel, no tin. We do have chloride ions, right? And we do have water, right? So one of those two is likely to occur, okay? So let's pause before we jot that down and go look at our actual reaction. So now, right, you can clearly see, right, that at one electrode, there's definitely bubbles over there, right, and purple, bubbles and purple. At the other electrode, right, if the lighting were better, perhaps we could see better, but you'll see that there is definitely something happening, right, in that the color of the paperclip has changed, but other than that, it's hard to really tell what's happening, right, but there, definite bubbles, definite purple, okay? So let's go ahead and take those observations and see if they make sense, right? Does the purple make sense in the bubbles? Right, that's this one right here. So here, purple, bubbles, right? Which means that reaction is happening there, right? So there we are getting the reduction of water to form hydrogen gas and hydroxide ions, right? And then at the other electrode, right, here is where sometimes the reaction doesn't really go the way we plan, right? So hypothetically, if we were oxidizing water, we should have gotten some bubbles, right? Or even if we were oxidizing chlorine, we would have definitely also seen some bubbles, right? But in our reaction, we don't see either of those really well, so hard to know. What's supposed to happen is we were supposed to reduce water, and so it should have been 2H2O gives us O2 plus 4H plus 4 electrons with a negative 1.23 volts, right? And again, if we look at the voltages, right, this one is less than that one, so that one should be the more likely one to occur, especially in a dilute solution where there's not a boatload of chloride ion. Yes, does that make sense? So you would sum these to get our overall cell voltage, right? The overall balanced reaction would be this times 2, and we would sum that together. So hypothetically, if this is the one that happened, right, we should have seen bubbles and what? Right, bubbles and pink, right? It should have turned pink to indicate the presence of H plus at that end. Now, if it had been chlorine gas, we would have seen bubbles. Would it change color? No, right? But what would we have noticed, those of you that are avid swimmers? Right, there would have been a faint chlorine odor, right? Chlorine has a distinctive odor, which we would have noticed should that have been produced, right? Obviously, we can't tell that through the iPad. All right. Number 2 says we have a copper electrode is submerged in a solution of acidified copper sulfate. The electrode is connected to a power source, and the other electrode is a nickel, also submerged in the same solution. So all of that is quite wordy, so let's go ahead and draw our scenario. So here is our scenario, right? We have one beaker, that's our copper sulfate. There we have a nickel, and there we have a piece of copper connected to a battery, right? So let's go ahead and doodle that as our cell. So here we have just one beaker. Here we have our aqueous CuSO4, right? And it does say that the solution is acidified, right? Now that serves several purposes, right? So what that means is there's an abundance of H plus in the solution, which does increase the ion concentration, which helps with conductivity, especially when we're doing it in one bucket, right? In addition, if I had opted not to use a copper electrode, that would provide us a secondary option for what reaction occurs, right? But anyway, and so we're going to have one electrode is copper, right? And we're going to have another electrode is a nickel, right? Which is also solid. And these are connected to a battery, right? Okay, so it says we're going to predict our reactions. So let's go ahead and see what's plausible. So first, again, the analysis is the same. We're going to look at what our options are, right? So copper sulfate. So note sulfate's not even on here, so we're not going to consider that. We do have copper, right? And note that we have copper solid and copper ions both present in my solution, yes? And not a lot of other options, right? So in the land of what might occur, tough call, right? So why don't we go ahead and take a look at our reaction? Oh, we did say it was acidified, right? Which means there's also some of this in the solution, right? So let's go ahead and watch the reaction and see what happens, okay? So you'll see that we take each of our electrodes, which are connected to our battery, and we carefully shove them into the beaker. Yep, I should have just used something, differently shaped, and that would be less annoying to have done, but that's okay. You work with what you got. I filmed all the demos on that Monday so that way I would have them all. So, you just work with what you got when you're trying to get so much done in one day. And oh my gosh, check it out. One electrode, we get the plating of copper, right? Because clearly that nickel was not orange to begin, right? And on that other side, right, clearly the nickel is now coated in copper, and that copper, the color has changed, right? Meaning that some of it has participated in the reaction, right? And so when we come back over here to analyze our cell, what that means is clearly at this electrode, what's happening, right? At this one, we're clearly getting the deposition of copper, yes? We're going from copper ions to copper solid, right? That's definitely happening there, right? Which means that's where our reduction is occurring, right? Which has a voltage of 0.34. So going back to what we talked about when we did the galvanic cells, the overall cell voltage needs to be negative, not necessarily each individual half cell, right? Then over here, right, we're actually getting the opposite reaction. That's what's happening, right? And that we are going from copper solid to form copper ions and 2 electrons, right, which has a negative 0.34 volts, right, which means that overall the cell voltage is 0, which is why we need to supply a little bit of power via the battery in order to make it occur. Yes, does that make sense, right? So the overall net reaction would just be the sum of these two together, would be the overall reaction. The sum of these two, which is 0, would give us our overall cell voltage. And so our observations help us to predict what would happen, right? All right, last up, it says we have a solution of tin 2 chloride is electrolyzed using inert electrodes. So again, inert just being the clue to you that you don't have to worry about what those electrodes are made of, meaning all you're going to think about is what's in your tin 2 chloride solution, right? Which is going to be some SN2 plus and some chloride ions, right? And it says to go ahead and draw the setup. So let's go ahead and get that cell. So here we have a little tiny petri dish that's filled with our solution, and we have 2 paper clips, and we have our stuff. And again, I don't know why it doesn't occur to me to just clip those paper clips on before we start the reaction. All right, so petri dish, electrode, battery, right? And what else? I don't know. Okay, and then our options, right? So there aren't a whole lot of options in this case, right? Just like the last one, which I think is what makes some electrolytic cells easier, right? So we know we have some tin. Oh, look, here are some options that deal with tin. Okay, and here is the important part. Which species of tin is present in our current solution? Right, the only thing present is SN2+, which means if we look at our options here, what's going to happen? Right, we're going to get the reduction of tin at one side and the oxidation of tin 2+ at the other side. So in this particular instance, just given our stuff that's present, that seems like the likely option, right? So let's go ahead and write that out, right? So we've got some SN2+, plus 2 electrons is going to give us some SN solid. We also have some SN2+ is going to give us SN4+ plus 2 electrons And that voltage is going to be negative 0.14 and negative 0.15. All right, so it does seem to fit, right? And so we'll be looking for evidence of that, right? We'll be looking for evidence of that and evidence of that. And so now, if we take a look, I'm going to move the camera in just a second. Now we can definitely see the formation of those SN solid being formed, right? And at the other electrode, right, we can see that something's again happening to the paperclip, but it's hard to see on the white background. So now I decide to move that paper towel. And lo and behold, we have solid on one side, and at the other side we see that there's the formation of a what? Of a precipitate, yes? At the other end we get the formation of a precipitate. Now, does that support this set of reactions? Yes, right? So we get our solid tin forming here, right? And here, this forms a precipitate, yes? As in like SnCl4 is a precipitate, and that's what that white stuff is, right? That's the sign, the visual cue that tells us this reaction is occurring. Yes, does that make sense? Now, just for fun, I did not write it in here, right? But what we're going to do is we're going to flip the electrodes. So you'll see that I'm going to detach them, right? And going back to, live things we should have observed, right? Batteries have specific ends, yes? Which ought to make sense now because a battery is an electrochemical cell, right? Electrons come out of one end and into the other, which is why direction matters. So now I've flipped the ends of the battery, and you'll see now tin is being formed at the other end. And what's happening on the other side? Right, instead of producing tin 4, now we're just reducing, or we are oxidizing that solid tin that was in there. Yes, there's less and less solid tin on that one side. Yes, does that make sense? Once we flip those electrodes, and so we flip where the oxidation and reduction occur. Yes, does that make sense? All right, life things we should know, right? Which, by the way, is the concept of like how your battery works, right? You deplete your cell phone battery all day, then at the end of the day, what do? Or some of you less than all day, I guess, depending on how much you use it, right? You plug it back into the wall, and what you're doing is you're basically flipping the switch on there, right? Forcing the electrons to go back to where they came from, so that way you can then deplete it again, right? Over and over again. But anyway, I hope this has made sense. I hope that you understand the concept of electrolytic cells and how they compare to galvanic cells. And yes, we could label the electrodes just like we did in the previous one. I just didn't. And super important, make sure you understand how the observations, right, correspond with the choosing the reactions. All right. Thank you for listening. Be good, and I will see you sometime soon, I hope. All right.